Hey, welcome, guys. Well, if you are watching this, then we are almost at the end of this road. This is our last lecture topic. So, what are we going to be talking about in this particular lecture? Well, that's an interesting thing. It's called Gibbs free energy. And Gibbs free energy is a way for us to consider a lot of the factors that we've already talked about this term to see if something is or is not spontaneous. So that's going to be our subject for today. But of course, we always have to start with our review from last time. So let's talk about what we talked about last time. Using the provided data, calculate the free energy of the following changes. I did not mean free energy, I meant entropy. I have to make some typo fixes in this. So when I say using the provided data, what I mean is let's go to D2L. So let me see if I can find D2L. And I'm actually going to do this. Content. Course documents. Exam handouts. Standard thermodynamic values. And this is that same table that we were talking about last time. So this is the same information that we were talking about previously. Okay, so the first one we want to talk about is form RbCl gas. RB from RB gas plus Cl2 gas to give me RbCl gas. And of course, if I'm going to do that in my standard format, I want to make 1 mole of that. So it's going to be Rb plus half of his Cl2 goes to RbCl. Okay, so we're going to look up some values for this. And I'm going to come down here. These are in alphabetical order for the most part. Rb, Q, R, R. I know where R is in the alphabet. RbCl, and this is solid. I only have values for RbCl solid, so I'm going to change this. For the love of God. Sorry, my technology is not working with me. So I'm going to change this from gas to solid, and I'm going to change this to solid. Because those are the only values I have to work with. Unfortunately, I can't calculate phase change if I don't have another value that I can work with. So then I'm going to look at my RbCl solid. The entropy there is 94.5584. 95.5584. Oh, it's 94.55. Sorry. 94. And that's an RbCl solid. Okay. Awesome. Now remember that we're talking enthalpy, entropy, free energy. So I talk about them in the same order that the data is presented. Awesome. That's kind of why I do it the way that I do it. When we talk about our Cl2, and we need to look at Rb gas, which is right here. That's the 169.99592. And then we need to go find our Cl, which is somewhere in here. Cl2 gas, 222.96536. 222.96536. And of course, these are all in joules per mole Kelvin. Okay, and again, my equation for this is the sum, and I'm going to write that here, sum of the number of them times the products minus the sum of the number of them times the value for the reactants, and that's my delta S naught. Okay, now this is, and the reason that I write this the way that I write it is because it's true for delta H, delta S, and delta G. So I don't like to have to remember that this is, I put in the delta H here and the delta S here. I just write it like this, and then I can label it however I need to in the front. So that works for me. Now, you will see, if you look in the exam handouts, you will see in our table that is on here, so on page 6, there is no equation that includes all of this. Why is that? Because they're all the same. Okay, so that is not included there because the expectation is that for this section, where everything is really theoretical and then we talk about a very few calculations, and since those calculations are all the same, the expectation is that you can remember that formula. Okay, but that is what we're talking about there. So just remember that that's the formula that you need to be dealing with. So if I want to look at my products, we have that 94.5584. That's my product. And I'm going to subtract the sum of my reactants. So I have 1 mole times the 169.99592 plus half a mole of 222.96536. Now remember that it is half of that, and that's because of the stoichiometry that we put in front of that Cl2. We have to multiply by that stoichiometry for this math to work. Okay, so that's the value that I'm going to be looking for. I have 94.5584 minus the sum of 1 times 169.9959. 2 plus 1 divided by 2 times 222.96536. And that gives you negative, and if my math is right, negative 186.9202. Okay, and again, that's kilojoules per mole, or joules per mole Kelvin. And of course, thinking about this, I'm taking 2 moles of gas, or 1.5 moles of gas, and turning that into a solid. So I would expect that to be a drop in entropy. So that's what we're talking about there. Okay, so hopefully that is cool with you guys. So again, this is negative 186.9202. That's joules per mole Kelvin. Okay, make TiCl4 gas from Ti and Cl2. So here I'm going to be taking, and I'm going to move this down here. I'm going to make TiCl4 gas. And that's my product. Oops. So I'm going to take Ti. Let's see what we have for Ti. So let's go look for our Ti. Who else has to say the alphabet to themselves to make them find it? Okay, now I didn't say, so I want TiCl4 gas, which is this one right here. Ti, we have as S, solid, beta, and alpha. I don't care which one you choose because I didn't specify. So I'm going to say, okay, I'm going to put this as solid beta. No reason why. Plus 2 Cl2 gas gives me TiCl4 gas. So that's the formation that I'm trying to look at. Now, my Ti solid in the beta sense has a delta S of 30.66872. And I chose the beta because why not? No, and actually, no, that's alpha. Sorry, and that is the one I meant to choose. And why did I choose that one? Because it says that the alpha has a 0 in the enthalpy formation, so that's its native format. So if I choose this value, that is from its native format. Now, I have no reason to do it that way That's just why I chose the one I chose. Okay. Now my Cl, and I'm going to take my TiCl4 gas right here, 354, 8032. And then let's go find our Cl2. And notice that I don't have any of these values memorized because they're not predictable in the same way that I would expect them to. Cl2 gas, 222. 222.96536. So products, I have 1 mole of 354.8032. And then I'm going to subtract 1 mole of 30.66872 plus 2 moles, 222.96536. And then that whole thing is what I'm going to subtract. So I have my 354.8032. I subtract the quantity, 30.66872, plus 2 times 222.96536. And I end up with negative 124.79624. And I haven't worried about the number of sig figs that I have. I'm just reporting the number that I calculated. In terms of what that number of sig figs should be, I'm looking, there are 1, 2, 3, 4, 5 decimal places past the decimal point. So any number that I have should be 5 past that decimal point. And that's what I see for almost all of these. I didn't get that for my 9202, which means I should be reporting that as well. Okay, so remember, since these are additions, we want to look at how far past the decimal place we should be. Okay, so there's that. And the entropy of formation of CdNH342 plus from CdN2NH2. Okay, I'm going to calculate that in just a minute. I want to talk about these other questions before I go to calculate that because I need a little more space to calculate that. So what does entropy mean? What is entropy again? It's a measure of the disorder in a system or the surroundings or whatever we're trying to talk about. It's the measure of the disorder. Does the entropy of the universe get more positive or more negative over time? Over time, we always tend to more disorder. So more positive. Okay, so just think about this. Think about your room for a second, right? Entropy is disorder. So if you leave your room without putting any energy in to clean it, does it stay clean or does it get to be a mess? And it gets to be a mess. We have to put energy in to make it more ordered. Okay, so we expect it to get more disordered, positive delta S over time. Does entropy alone provide enough information to determine if a reaction is spontaneous? No. Does enthalpy? No. Both of those are no. And that's why we're talking about this topic today. So that's where this next topic will come in. But remember, if I ask you, is it enough on its own? No. The answer is no. I cannot do it from that alone. Okay. Now, let's do one more calculation. So we want to do a calculation for CD plus N2 plus H2 to give me CD NH3 4 2 plus. So I need 1 CD to make that happen. I need 4 N2s, so that's 2 of those. 12, so I need 6 of those. Okay. CD is a solid, this is a gas, this is a gas, and this component is aqueous. Okay. So let's go find our CD, because that's probably the closest one to where we are. CdCN4 the CdNH3 2+, that's aqueous, which is what I would have expected. My entropy on that is 336.3936. Now you may remember that we talked about formation constants back in the day when we talked about equilibrium constants. We said that certain metals are more soluble in the presence of other things, like ammonia. And that's because they can form these weird complexes that have charge on them, that have a bunch of these things on them. And so the metal goes into solution, and so you can dissolve more of that insoluble salt because of that. This is one of those compounds that we would calculate a K of formation for. And we would do that by multiplying the KSP times that K of formation to get an overall K for that process. All right. On my CD solid, and again, we have a gamma and an alpha. I'm going to choose the gamma because it's the one that has an enthalpy of 0. So it's the one that exists in nature. So 51.75608. And it turns out that they have the exact same entropy value, even though they don't have the same enthalpy. Let's go find our H2, because that's the next thing we're going to run into. H2 gas is 130.56586. 824. And then let's find our N2. N2 gas is 191.50168. Okay. So again, products minus reactants. I have 1 mole times that 336.3936. And then I'm going to take, and I'm going to subtract from that the sum, total value of 51.75608 plus 2 times the 191.50168 plus 6 times the 130.586824. So again, I have 1 CD, 2 nitrogens, and 6 hydrogens to make that product that I'm looking for. So I'm going to do some simplification, 336.3936, and I'm just going to subtract 51.75608 plus 2 times 191.50168 plus 6 times 130.586.824. That's 1218.28038.4. So 336.3936 minus that answer gives me a negative 881.886784 joules per mole Kelvin. And that makes a lot of sense to me. Looking at this reaction that I'm doing, I'm taking all of these individual components, CD, 2N2 gas, 6H2 gas, and putting them all together into this one aqueous component, okay? So that's not going to be an overly favorable process. Right, so that's the value that I get from that, and that makes a lot of sense to me. Hopefully, that makes sense to you too. Questions, comments, problems, concerns, anything like that. Okay. Well, then I'm going to take a break here. Maximize this. Take a break and get us set up for the next part. Talk to you soon.